Welcome everyone to the Support Vectors research paper reading series. I apologize, I have been absent the last few weeks, but we'll try to continue our paper readings a bit more regularly. Though I must say, the next couple of weeks may become tutorials on various topics rather than paper readings. But be that as it is. Today's topic is energy-based transformers are scalable learners and thinkers. This paper has a pretty distinguished pedigree. If you look at the kinds of people who have done that, there's Harvard University, Stanford, UIUC, and UC, Amazon, University of Virginia, I believe. And there's a long list of authors to this paper. I'll give you the gist of what this paper is saying, and then we'll go back and look into the details. What it is saying is that there has been two independent streams of activity. One are the transformers that we are all familiar with. We have been doing a lot of research paper readings around transformers. They have been around since June of 2017. Attention is all you need, and the rest is history. The GPTs and all of these are transformers. They have had steady evolution. Nevertheless, they have had specific problems. For example, it has been relatively hard to induce genuine thinking into them unless you're talking about very specific, verifiable domains like math and coding. So at math and coding, in recent months, for example, since deep sea carving came out, people have realized that you could induce what could be called a simulacra of thinking, or maybe genuine thinking, into these models simply through reinforcement learning with verifiable models. But that is not generalizable to other areas. For example, you can't easily generalize it to law, to history, and to other things. More importantly, it is hard to generalize that reasoning ability to different modalities. For each modality, you have to do something specific. So reinforcement learning with verifiable rewards or other similar techniques, long chain of thought examples, and so on and so forth, are not quite successful in generalizing thinking to multimodal situations and wider applicability. That is one issue that they mention is the current state of the art. The other point they mention, which has been noted by researchers recently, is when you look at what reinforcement learning with verifiable feedback does, there seems to be growing evidence that, not complete proof, there seems to be growing belief from some experimental data that these models don't learn new things. The reinforcement learning simply accentuates and sharpens whatever the model has learned in the pre-training or in the supervised fine-tuning. But they don't necessarily learn absolutely new things. Now, that itself is a debatable position. It is not quite written in stone. And I, for one, don't fully subscribe to it. But there seems to be a belief that is so. Those are considerations. Those are the shortcomings of transformers. The strengths of transformers are they're massively parallelizable. They and all the things. They remove the deficiencies of recurrent neural networks and so on and so forth. So then there's another class of models and theories called energy-based models. Energy-based models have been around for a long, long time, ever since the Hopfield network. And one can reformulate or think of most of machine learning as implicit energy-based models. Or for example, we can think of generative adversarial networks and so on and so forth as energy-based models. I would call them, what these authors call them, are implicit energy-based models. And then there are explicit energy-based models. What what energy-based models have you come to? But the explicit energy-based models are those models whose purpose is to predict. The output of the model is an energy function. It is uh, not a prediction directly per se. And energy-based models have been around. They have been hard to train. They have been hard to scale up or parallelize and so on and so forth. There have been various explicit energy-based model efforts. The core idea in this paper is, how about we take energy-based models but implement them through transformers? So it would remove the deficiency. You would get the parallelization, you would get the ease of training, the experience of training transformers. And now you hybridize that with energy-based models, which a lot of researchers have believed for quite some time are a superior way of thinking. Many researchers have hypothesized that the way to thinking machines, the way to generalize AGI, somehow will go through energy-based models. Many people have hypothesized that. So this is along those lines. What is the energy-based model? I'll talk about it in detail. Now, what they show, first caveats to it, they have experimented with very small models, not even a billion parameter model, I believe, it's smaller. And so we don't know whether these results that this paper brings up will remain true when you scale it up to frontier model sizes. That is subsequent research work to be done. Nevertheless, there is considerable merit in the ideas that they bring to the table. And so I would consider this to be a concept or an ideas paper. And they have some interesting results with those small experimental models that they worked with. And those results are quite encouraging. They find that these energy models, like the title says, they're scalable learners, and they also are thinkers. Now, when it comes to thinking, people in cognitive psychology talk about system 1 and system 2 thinking. System 1 thinking is reflexive, intuitive thinking, fast thinking. Intuitive, fast thinking is system 1. I'll just write it down. System, okay, this is too hard. System 1 is, I apologize, something weird. We went back to the previous paper somewhere. Okay, there we go. System 1 thinking is fast, intuitive or reflexive thinking. It dominates our thinking process. So, for example, we reflexively enter a room and with very minimal or no thinking, turn on the light. We know that the room is dark and we should turn on the light. Or we know that if the refrigerator doesn't have enough vegetables, it's time to go to the grocery store. On the other hand, there is a talk about system 2 thinking. And there's a landmark book that I highly recommend people read, Thinking Fast and Slow. That popularized these concepts. The author actually got a Nobel Prize. So system 2 thinking is slow, deliberate, reasoned thinking. For example, if I were to give you a problem, let's say find arithmetic problems, for example, are often system 2 thinking. If I were to give you a differential equation and say, now find the solution to the differential equation, reflexively, you would take up a piece of paper and start thinking slowly about what's the optimal approach to solving that differential equation. That is classic system two thinking. Or if I were to say, is it a good time for you to change the job? Are you safe in your current job, given all the layoffs that are happening? It is the kind of thing that will cause you to ruminate for some time. Look at the probabilities of your getting laid off. It will help you ponder what's your performance, what contributions you bring to the company, and all things considered, are you likely to be laid off? And even if you're not, is it a good time to look around, and so forth? So that's system two. So this paper says that so far the transformers have excelled at system one thinking. They do very well that. But the goal, the contemporary goal is to do system two thinking. But when you do system two thinking, to do it for multimodal, is there an approach that is multimodal, right? And scales well and so forth, scalable? That gives you other good properties like confidence, that tells you how confident it is, or verifiable results for domains outside coding and math. So as you know, the DeepSeek paper, DeepSeek R1 paper, created the remarkable result that with RLVR, reinforcement learning with verifiable feedback, you could induce a system to thinking for coding and math problems. But could you do the same beyond those two domains for a broader domain? So this is the goal. And what this paper says, that they are making a contribution with a model, with an approach that takes you closer to that. So that is the gist of this paper. Now, this paper uses terms like energy-based models, etc. That needs a little bit of a primer. And so this paper is to be read sort of backwards, but we'll do that. I will actually start with the appendix, where they give you a small understanding of energy-based models. Autoregressive video. Let's go to the appendix. I believe it's appendix H. So it's a pretty long paper and a relatively dense paper. So I'll keep to the key highlights, and I'll try to explain the main ideas in the paper as best as I can. And FGH, we're getting close. Okay, so a simplified energy-based model introduction. What it is saying is, this picture I was coming to. See, in a typical LLM, what you get is you feed in a input. So input could be, let's concretize it. X is the happy cow jumped over the, right? So this is your prompt or input prompt. And your model is trying to predict the next token. Right? And you would imagine that this Y hat ideally should be the word moon. Right? So that would be a feed-forward model. So it's your basic model. You feed it into an LLM or any kind of a model in a single pass. This goes in, and what comes out is Y hat. And that Y hat hopefully is the token moon. Right? Or either it's the token moon, or it is somehow pointing indirectly to the token moon, giving it higher probability mass or something to that effect. That's your standard. Now, what the energy-based models do is quite interesting. They say that energy-based models don't actually make a direct prediction. They do something quite different. And that is if you're not familiar with energy-based model, this will come as a surprise to you. If you give it an input, you make a guess to the output. Just randomly pick a guess. Let's say that you pick a guess y hat, right? A prediction. And what you do is you feed this to both of these into the energy-based model. And what it will produce is a scalar value, which is fancy way of saying it will produce an energy. And let's say this energy-based model, the parameters of the model are theta. Basically, think of a large language model for the sake of this paper. And these are the parameters of the model. It will produce an energy, E, which is just a real number, -1, -2, 3.5, plus whatever it is. Think of it as an energy, an unnormalized energy value. Right? And now, the moment you talk of energy, you start thinking, if you're familiar with the literature of energy, you start thinking of the Boltzmann equation. Right? And you start thinking of probability or the unnormalized probabilities. Let me just say, probability of x, y hat, essentially to be right, to be proportional to e to the minus t theta of x, y hat. So this equation is actually the crucial idea. Let me explain what it means. Remember, I'm using a proportionality constant here. Now, see, the basic idea is if y hat is the best answer, or the word that you use is most compatible answer, then the energy E theta will be low, then E theta will be low, else high. In other words, for bad guesses, the model will produce a high energy state, a high energy value. And for good answers, it will produce a low energy value. It just produces a number, a real number, a low value. So theoretically, if you're saying moon, the happy cow jumped over the moon, then in our way of thinking, roughly speaking, the energy state of that should be far lower than the energy state of feeding in the happy cow jumped over the, let's say, cabbage, right? Or jumped over something else, the water or something else. Right? So those would be higher energy states relative to it. So what the energy models learn is to predict an energy function. It's an energy function that just tells you, make a guess and we'll tell you how good the guess is. So now this raises a very interesting question. In a vocabulary, let's say that you have a vocabulary of 30, 40,000 words or a million words. Does it mean that I have to go and guess, feed in one word at a time, and then see which word is most compatible to, or which token is most compatible or have the lowest energy, so that I call that the next token prediction? That's the first question that would come to mind, isn't it? That if you give me an energy function that just tells how compatible is this token with respect to the prompt so far, then the task remains. I need to sort through, somehow find a way to run through the tokens and find which token is the most appropriate. Well, the good news is, because energy is a model, it's a function, and we can feed in tokens as not as tokens themselves, but as something different, actually a probability function, which itself is shapeable. So all you have to do is, and this is the key insight it says that, see, what you need to do is, this model needs to pick a point to a probability distribution over the token. So here's the word aardvark. Here's the word, last word, let's say zephyr. This is a probability distribution over the tokens. Now, and let's say that it is speaking on the word moon. But let's say that you randomly started out with another probability distribution. Sorry, like this, which is more or less random probability assigned to each of the tokens. If you just randomize, give each of the tokens a random probability, what this machine is saying is, to get to the word moon, you would follow this journey. You would gradually shape. So, and this is the interesting thing, at inference time, and this is the key thing with energy-based models, at inference time, do gradient descent learning to shape the pink line, pink initial distribution into the white final distribution. You see that the white final distribution has put most of the mass here around the word moon, isn't it? It has really peaked, or perhaps an even better distribution could have been even more peaked. So let me make it even more peaked. Let's say that, sorry, let me make it more peaked in a white distribution. Sorry, I'm erasing it. What am I doing? I'm erasing things. Let's say that the final distribution becomes like this, where you see that it is heavily peaked around. Most of the mass is peaked around the word moon, right? Whereas the initial distribution was the pink. What is my pink line? Okay, was the pink line, right? So this is very interesting. What it says. So what we need are two-step journey, and this is a point that is crucial, and I want to mention because it's not so. Some of these steps are not explicitly given in the paper. What you do is, if you're doing next token prediction, you would just start with some random probability distribution. So start with you call it your first prediction, your y hat. Y hat 0. Y hat 0 is just sampled off a noise. Just sample it out of a noise. And so you will get, most likely, you'll get a probability distribution over the vocabulary, which is more or less perturbations around the same value, right? Then what happens is that you do, now from this probability distribution, this is a probability distribution 0, how do you go to something that you can feed into the energy function? Because the energy function is taking the input token vectors, so the context vectors. So you can convert the input text, the happy cow jumped over each of those tokens, you can convert it into vectors, word vectors. So let me just call it context vectors or prompt vectors. And the y hat, we need to feed it. Let me just call it PD hat. Somehow we need to produce a y hat, another vector. We need to feed this because obviously these two will go into an LLM. If you think of a GPT or something like that, a tokens go in, right? Or tokens or the embeddings go into a transformer. So we need to somehow convert it into a transformer. And this part actually, at least I feel the paper glossed over. And so I would like to go over it in detail. The way you do it is, you do a dot product between the probability distribution, a dot product with the token vectors. or token, or let me call it vocab vectors. Your vocabularies, all the vocabulary vectors, which is all the way from aardvark to Zephyr. So what it basically says is that, let's say aardvark is pointing this way, and Zephyr is pointing this way. Let's say that this is 0.9 and this is 0.1, just for the sake of argument. Then you would agree that a weighted sum, so this is a weighted sum, a dot product would be a weighted sum, would more or less point more towards aardvark than towards Zephyr, right? But in any case, you have ended up with a y hat 0, initial y hat. Now, this is the y hat that you will feed into the energy function. And what the energy function will say is, okay, I tell you a value, 70 or something like that, a number. This is the energy, or this is the compatibility, or actually I would use the word incompatibility measure. Let me just write this word, which the paper doesn't use, but I'll use it. Energy function measures the incompatibility between x and y hat. But y hat implicitly means between x and the probability distribution, PD, that you have taken up. Because out of the probability distribution, it helps you, it guides you towards some word vector. And it is basically saying that's not very compatible. Right? The more the incompatibility, the bigger the energy it will produce. And now your job is, because this probability distribution is learnable, because this you can, it's a tunable, it's something that you can change. Therefore, at inference time, assuming that the model has been fully trained, then at inference time, what you do is you can gradually use gradient descent, the usual gradient descent, use gradient descent at, and this is the most important thing, at inference time to gradient with respect to what? With respect to whatever probability distribution you took, and therefore whatever y hat prediction that you made. Of the energy, you can say energy remains the same. Energy function is there. What is the energy function? It's a function of theta. So you're not, at inference time, you can't change the parameters of the model. But what can you change? You can change the shape of the probability distribution. And by changing that, you can change y hat, the prediction. And so you're saying, how do I change the probability distribution and therefore do a gradient descent on the prediction itself to come to the best prediction? So y hat at t plus 1 is y hat at t minus alpha. This is your standard gradient descent step. Observe that the gradient is taken with respect to the prediction itself, right? And therefore with respect to the probability distribution. So what it is showing is best represented with a picture. And now I'll go back to a paper and start from the beginning. But before this, I would like to show one of its illustrative pictures. And this will come to, yes, I'd like to show this picture clearly. See, let us see that the model has been trained. Assume that the energy-based model is trained. See what is happening. You are giving it step 0. Now, or rather, actually, let me something. Observe how at step 0, look at this initial guess. You realize that this is more or less sampled off the normal distribution, right? There are words. The dog caught the, now the right answer is frisbee. But in the beginning, if you just randomly sample off noise and give probability masses to all the tokens randomly, You would agree that now, please pay attention to where I drew the green line. I don't want to. Would you agree that this is more or less random? Now what you do is you say, how do I reshape this probability distribution? Because look below, look here. I wish I could blow this up more. Does it allow me to blow this up more? Let's see. Any bigger? No, it won't let me make it any bigger. So please pay attention to this part. Do you notice that this dot says that this probability distribution is actually a pretty high energy state? Bad guess. Right? So then you ask, okay, let's step by step reshape this probability distribution to something better. So what do? You do gradient descent. You see the black dot coming down the energy function to a minimum. So this is the gradient descent iteratively. And what happens? You would agree that now this is a slightly better, step one is a slightly better probability distribution. Step two is already beginning to focus on the word frisbee. Step 3 looks even cleaner. And by the time you reach step 4, the machine has very, very high confidence that frisbee is the word because it has accumulated all the probability mass and put it on the word frisbee. So one way of thinking of probability distribution is just one unit bucket of sand. That sand was spread over all the words, but gradually, as you gain confidence that the word should be frisbee, you're piling it up on the word frisbee. But remember, what did the energy model do? Energy model was always this function, E theta, right? The input was the same. If you think about this, the input here this is X. X doesn't change. So what was changing throughout the process? The only thing that was changing throughout the process was this distribution, Y hat, right? Actually, Y hat is not the distribution, but it emerges from the distribution. It is this distribution that is getting reshaped, right? So what you do is the same energy function remains, input remains, but at inference time, you do many steps to find out where exactly the probability mass will accumulate, which token will it accumulate on. And wherever it accumulates, that token is what you predict. So now, let's think of the consequence of that. What it means is that in a normal next token prediction, to predict one token, you have one forward pass in an LLM, right? But in an energy-based transformer, what you are doing is just to predict one token, you are in essence doing a gradient descent on the energy function because the model is not giving you the answer. The model is giving you a way to find the answer. And it says, do a gradient descent on the energy function, and you will soon figure out what your prediction is. That is the thing. So now you can ask, well, is it really justified? How much does it blow up computations? As later on in the paper, they go on to show that actually it doesn't. These are highly scalable things. And generally, the number of steps is very small, 4 to 6, sometimes 2, 3, 4 to 6, 10 steps, which from a compute perspective is negligible, right? So you can quickly run through and do that. But the crucial question, for example, in a talk that the author gave, one of the authors, the lead author, Alex, gave, is that, see, he posits this, the way he posited it is this. He said, see, suppose it costs you 100 times the compute to gain 1% better reasoned answer. Would you be paying the compute cost? Would you be willing to pay the compute cost? And he goes into quite a discussion, but he says that today we live in a regime in which when we train the LLMs, there's so many parameters. Almost always in training the LLMs, we end up with a zero loss regime. By the time the model training progresses, after a little while, you realize that losses converge to zero, which may be partly overfitting and so forth. But zero loss doesn't necessarily mean that your model is perfect. In fact, they are very imperfect, as we know. So the statement that the author makes in the talk is, he says, see, we live in a space in which data is scarce. We don't have enough data to train the model. So what we need is a data efficient model training, in which from less data you can get good or better answers. And his claim is, as he shows empirically, his and all the authors put together, the claims of the authors is, and they show graphs and etc., that at least for the model sizes that they deal with, it is clear that you get better answers, even though, and especially you see more of system 2 thinking, even though for every token prediction, for example, for words, you have to do a multi-step gradient descent. That is the crux of the paper, and they show that this thinking is multimodal. It not only is true for text, it is true in the continuous domain. For example, it is true for images and videos also. So for example, look at this video. Suppose you get these 3 pictures of the dog, and I'll let you look at these pictures. What seems to be happening is this dog is beginning to jump, right? It is beginning to jump. There is a frisbee there. In the first picture, the frisbee is in the air. In the second picture, dog has come closer to the frisbee. In the third frame, the dog is beginning to jump towards the frisbee. So logical progression says that the next picture should be that the dog has caught the frisbee. So see what happens. Once again, if you give it noise, you start with noise, and you give it to the energy-based transformer, it will say, oops, not at all, high energy. And so you need to do gradient descent in this space, which is now a continuous space of pixels. In this continuous, very high dimension space, you can do a gradient descent in response to that energy function to come up with step 1 image, step 2 image, step 3 image, and step 4 image. Now, one of the remarkable things they show is that it is very compute efficient actually, because when you do this, compare it to diffusion model, they show subsequently in the paper that while diffusion models take a few hundred steps to produce an equivalent image, this approach actually produces in 3-4 steps, and that result is remarkable, and it is worth looking at before we go into the details of this model. I apologize that I'm going back and forth, but I realize that to explain this paper, it probably worth going back and forth. Let me go to the actual frame. Where is that thing? Oh, limitations. No, I think I skipped past that.
As if there are some questions in the chat.
Okay, I'll take the questions in a minute.
Okay.
So look at this picture, guys, figure 10. You see that the energy-based transformer in 3 steps comes close to the ground truth. This is the ground truth image. Now, you notice that in 3 steps, the energy-based transformer has come up with a pretty good reconstruction. But if you look at this diffusion transformer, DIT, which is the state of the art these days, very close to that, it has taken 300 steps before it reaches anything close to a truck. Right? At 100 steps, it is still pretty noisy. Right? And the same thing you see for the second image. So anyway, so it does show the effectiveness of this method and its generalization. So first thing notice that the same approach is applicable to multimodal situation, to discrete textual situation, to videos, and obviously as a corollary to images, and I suppose to audio. So let me take the questions. Please go. Samantha, could you please repeat spell out the questions for me?
There's one. Do we need to prevent overfitting in this energy-based method? How can we do?
That's a very good question. How do we prevent overfitting? See, this the way I look at this paper or this approach is all the problems that you have with traditional machine learning, they remain. This approach is orthogonal to that. So, for example, how do you prevent overfitting in a traditional neural network? What you would do is make sure there is more data than there are parameters. In a prior paper, if you remember, we realized that every parameter has approximately 3.6 bit of memory. And so you have to overwhelm the memory. You have to show it more data, far more data than the memorization capacity of the model. And when you do that, you overwhelm it and you push it from memorization domain, overfitting domain, to the generalization domain. So that's the broad state. Do we have the luxury of a lot of data? Yes and no. These days we are training machines with trillions of tokens. So where are we today? It is reasonable to say that they are mostly generalized, though some level of overfitting still, residual overfitting still remains. But that is sort of those regularization techniques are somewhat orthogonal to this. What is applicable to other approaches are still applicable here. You cannot take a ginormous energy-based model and take much less data because you'll still have overfitting. Right? So that consideration remains. Nevertheless, this actually paper introduces a very novel concept. It is called energy landscape regularization, a different kind of regularization, which in some sense, what it says is that it is more data efficient. With lesser data, it can generalize faster. So perhaps it answers your question. It does improve the overfitting problem. It improves upon that a little bit. And, next question.
There's one. Will we use covariance matrices in this algorithm?
Will we use covariance matrices? Covariance between what and what? I'm not clear where covariance matrix came in. Could the participant
say how between sequential data?
Covariance between the sequential data. I apologize, I don't quite follow. See, you have tokens coming in. Let's take the happy cow jumped over there. So here we are doing a correlation or a covariance matrix between, I'm trying to understand which two elements. So take this as an exemplar. The happy cow jumped over there. And now the machine has to come up with the word moon. So where is the covariance matrix?
I think maybe covariance can happen between sequential data because I think the words after cow could be moon or hill, and based on the past experiences, there are some probabilities. So I think maybe there are some covariance matrix between them, among them.
I would say the compatibility matrix. You could say that given the input, more like a compatibility matrix between all the words that come out, all the tokens, like what is the most compatible at this particular moment. And that, yes, that is exactly what the energy-based model is. It's a measure of compatibility.
Yeah, I see. Thank you so much.
Yeah. All right. So let's go through the paper. It's actually a very interesting paper. So one thing, this word energy, and I will start here because it's a background to this, and I'm going into it. See, a lot of the energy-based arguments come from statistical physics, from Boltzmann distribution, which says, broadly what it says is that if you take ensembles, so just think molecules and randomly bouncing around, right? Or a drop of ink diffusing through water, or whatever it is, the molecules of water, ink diffusing through the water, molecules of water, then any given configuration of that ensemble of molecules has a certain probability of, has a certain energy state, first of all. Right? There's a certain energy state there. And then, based on that energy state, there's a certain probability that that ensemble is in that energy state. Right? So that is the thing. And the general idea is the higher the energy, the lower the probability. So that, I mean, I'm sort of slightly butchering the whole thing, but it does convey the gist of the idea, and I'll just put it here. If you look at the numerator, e to the minus e theta. So first of all, you realize that if you negative exponentiate anything, the value of the negative exponentiation will go from 0 to infinity. It will only be positive, isn't it? For example, if e theta is infinity, then e to the minus infinity is 0. On the other hand, if e theta is 0, then e to the minus 0 is 1. Okay? So it goes from, actually, e to the minus theta, if it is 0, energy is 0, then e to the 0 is just 1, right? Then there is a z there. The z has a fancy name. It is called the normalization partition function. What is its job? Its simple job is to make sure that all the probabilities add up to 1. Right? So when you do exponentiation of any bunch of numbers, there will be some values from positive values. You do want to make sure that those positive values ultimately, if you want to call them probabilities, all of those probabilities should add up to 1. And the only way you can do that is you'll need this normalizing constant in the denominator. It's called the partition function. Now, people often, whenever people write this equation, you'll find throughout machine AI literature this statement, more or less this statement said in many ways. It basically says that defines a probability distribution using a Boltzmann distribution, this, where z theta is the intractable partition function involving an integral over all possible values of x. Means, what is x? The state of the molecules or the ensemble. Right? And now, the number of states possible are massive. Like, these are numbers like 10 to the power 100 or 200, or bizarre numbers. Right? So you can't do such integrals. So when you can't really do an integral in practice, but in theory you see you must do it, those integrals are called intractable. It's an intractable integral as a partition function. Now, how does it relate to us? What we are saying is, any particular, like, given the vocabulary, you can create infinitely many probability distributions over it. Go on sampling, you can shape it. It's a continuous shape. And therefore, you're again in that space where you need that integration. So the way they solve this is, and this is often done in energy-based models, they say, forget the z theta. We don't need the equality. We just need that. We are just comparing one energy state versus another energy state. So who cares about it actually being a probability? So we say that these are, people often use sort of contradictory words. They're calling it unnormalized energy-based models or unnormalized probabilities, right? So this is not really probability, but they still use the word p theta. You're saying to give the intuition that the higher the energy state, the lower the p theta will be, the low likelihood it is of being the right answer, or the lower the compatibility it is, right? So p theta is in some sense a measure of the compatibility, if you want to. And E theta is a measure of incompatibility. Right? So with that definition of energy, and that's not, I mean, it's just relating it to existing literature, machine learning literature, and energy-based models. And energy-based models, by the way, a lot of people are very, very excited about. Jeffrey Hinton, Jan LeCun, and a vast armies of researchers in the field have been very, very enthusiastic about energy-based models and believed, as I said, that the path of AGI may be somewhere through the energy-based models. How is anybody's guess? So with that now, let us go and read this paper, and I think it should be a fairly quick read. I will leave the results as assume that the results are very good. So let's focus on the main idea, because somebody requested that this paper was a bit hard to understand, and could I please focus on explaining the paper itself, and especially how you train such a model. So I'll read the abstract. Inference time computation technique analogous to human system 2 thinking. So now we know what system 2 thinking is. Have recently become popular for improving model performance. However, most existing approaches suffer from severe limitations. They are modality specific. I work only in text, etc. A problem specific, for example, verifiable domains like math and coding. We talked about this problem, or require additional supervision training on top of unsupervised pre-training. So for LLMs, what do? You pre-train a model and then you do supervised fine-tuning and some RLHF, etc. So it is talking to the limitations of the state of the art with respect to system 2 thinking. In this paper, we asked the question, is it possible to generalize these system 2 thinking approaches and develop models that learn to think solely from unsupervised data? Namely, somehow in the pre-training like step itself, you can do that. You induce thinking in that step itself. Interestingly, we find the answer is yes. And by learning to explicitly verify the compatibility and then reframing prediction problem as optimization with respect to this verifier, that is the crucial insight. What they say is that, see, if I have an energy function, it is basically a verifier that tells me whether my answer is good or not, isn't it? So I can always use it to make a prediction. All I need to do is feed in a sample of answers and pick, and then do gradient descent for each of them, and then pick the minimum of the, even if there's, if the energy surface is irregular, if you start from m random points and gradient descent, then you will end up with m gradient descented minima and take the minima of the minima, and that will be a prediction. And in a way, you have verified along the way that your prediction is actually good. Your model is telling you that this is the best prediction you can make. This is to be contrasted with normal LLM. In a normal transformer, what happens? It predicts a token, but it also tells you the probability of the token, how much confidence it has, and you can't do anything about it. If it says, here's a prediction, and the happy cow jumped over the hammer, but my belief in hammer is rather low, but it's the best I can do, then you can't do anything about it. Whereas in this model, it will tell you that I don't have confidence in the answer. Try looking for a better answer. And there is a way to get to a better answer. That is the key. So specifically, we train energy-based transformers, a new class of energy-based models, to assign an energy which is unnormalized probability. So p theta so there's a little subtlety here. Maybe I would have worded this thing differently. There is a E. E is the E theta given an input and given a possible prediction is there. So you can give the prediction of y hat given theta is proportional to e to the minus x y hat. That's a point. Unnormalized probability value. So it's energy and assigned. So it is not, these two are not the same. Energy and unnormalized probability are not the same. They are related by this equation. A value to every input and candidate prediction pair, enabling prediction through gradient-based energy minimization until convergence. This formulation enables system 2 thinking, etc. Now, I won't go into the results, but let's go into the introduction. So this picture, I will just review the paper through pictures because by now it should be relatively clear. A typical autoregressive transformer, what do? You give it t tokens, and the feed-forward transformer will predict the t plus 1 token. Right? The next token it will predict. How does a RNN work? You produce the first token, it will produce a state. Then you give it the second token, it will produce a state. And you keep on giving all the tokens, and then you ask it to produce you decode the latent state to get the next one, the RNNs. Our diffusion models are a little bit more complicated, and this picture might not be doing the best justice to it. Basically, if you look at the forward diffusion process, what you're basically saying is x1, x2, etc. If this is the state of your image, right? You're basically saying that to produce, you know that the next image in the forward diffusion process is a noisier image. There is noise in the image injected. And if you can predict what noise was injected, right, then you have essentially figured out the next state of the next addition to be made to the image, right? That's that. So diffusion is a little bit, let's keep this aside if we didn't get the whole point. Now, energy-based transformer says what? Take X, come up with your Y hat, your next token, a candidate Y hat, pass it through the energy-based transformer. It doesn't produce, unlike A, contrast these two, unlike the autoregressive transformer, it actually produces an energy function, E theta. That's what we have been talking about. So that's the point. Now, it says it in many ways. And one of the primary goals of AI is to figure out how we can create systems that learn to think on their own, etc., unsupervised. So they talk in terms of three core facets, though there's a belief, at least one researcher, Yannick, hypothesized that they first came up with good results and then they sort of reverse engineer these facets because this model meets all those facets. But anyway, they speak to the strength of the model. So one is dynamic allocation of computation. Why? Because think about it this way. If the machine is not sure is very sure, let's say that you have the happy cow. Let me again write it. The happy cow. This is what you have to say. And for this, let's say that the energy landscape has a steep minima. What happens? You can start with a random state. You can do hop, 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 hop. And very quickly you'll get to the right answer. Right? And you can see that the valley is pretty steep. You have pretty high confidence. You quickly get to the right answer. On the other hand, if you say what is the word here? Now it could be anything, right? And suppose you say quick, you tell it, now what? Quick, let's say that the thing is, and the statement you're trying to guess it, quick brown fox. Right? Now, the quick could be anything. So you would imagine, you would hypothesize that the energy landscape might be pointing to the word brown, but it is not very steep, it's shallow. So you would have to make lots and lots of steps. It will take you a long time to reach that. And not only that, because the energy is measurable, you would in effect know that the machine is not very confident of its own answer at this moment. So that's the point they are making. Dynamic allocation of compute, or modeling uncertainty in continuous space. This is the second point. As you can see, you can model uncertainty by how steep, how deep, or what's the energy. What is the energy that you finally achieve? A verification of predictions. How do you verify the prediction? Verification of prediction states, very simple. To verify there's the lowest energy state, you can verify by starting at, let's say that you have this loss landscape. Let's say, I'll just draw it out, and there is a deep valley here. Let us say that you started with this point. And let me deliberately give it multiple minimums. Like this. And some sort of a multiple minimum. So now what happens is, let's say that one point went and got stuck here. Another point got stuck here. Another point went all the way here. through the gradient descent step. Because as you will see in the algorithm, you always do a argmin of the minima. So which minima is the minima after gradient descent? A, B, C. So you would say that obviously argmin energy is for A. So I will pick A as the answer. Right? So that is what they are talking about, the verification of prediction. Right? And then, so this is it. They talk about this as and this picture is crucial. So again, I'll blow it up. See, observe that here you start out with random guess, a very randomly shaped probability distribution. That represents your point here. Then you go to step 1, it represents this point, 1. This is your next probability distribution. You're doing gradient descent in the energy space. 2, you come to this, you're pretty much there, 3, and then 4, which is right here. And this is the gradient descent space, descent that you're doing in the energy space. Right? And what is the flow? What is the axis of the axis of this? The z-axis is, of course, the energy. What is the rest of the axis? It is literally a probability distribution dimensions. Right? For example, it could be all the tokens, the vocabulary tokens, and so forth. So that's the basic intuition. And let's look at the two core steps here. Inference with verification. Look at this. So what is the input? You have given a context. These days we call input as context or prompt. The word context is taking over. Instead of using input or prompt, a lot of people are using the word context. So you give X, you have an energy-based model already trained. So given an input X and a candidate, a guess, it will produce an energy. What you do is you use hyperparameters of the model is how many steps you want to take, what's your learning rate, and what the sample M is. Now, remember, guys, if you have already reached a minima, then ideally gradient is disappeared. So there may be some steps that are wasted. Let's say that you set N to 10, but in 6 steps you're already at the minima, then no harm done. 7th, 8th, 9th, 10th step will be just wasted. Right? They will not lead to much movement. So what you do is you sample off, you take a random distribution, So what you're doing is you're assigning random weights to the sample from a normal distribution to each of the words in the vocabulary. Then you do it for n steps of gradient descent. What do? Look at this. This is your core inference time gradient descent on the prediction space. Remember, not on the parameter. The model is not changing at inference time, of course. You are changing your prediction. Oh, sorry, not the prediction, but the probability distribution. You are changing that. So this is the crucial step. Remember, you're coming up with a better prediction candidate, and you keep on doing it, but you do it for m steps. You realize that, right? Samples. So you start with m samples, and what you do is look at the outer loop. You do it for each of the m random starting points. And for each of the starting points, you do gradient descent. And this is the final key thing, which is the verification part. You can call this the verification part. That it will tell you that your final probability distribution is whichever is the best amongst those m sample points. And the crucial insight in this paper is you learned a verification, the energy function that you learn, that you're using, automatically gives you a prediction. Prediction is a consequence of learning the energy function, which is the verifier, which gives you the verifier. Now, the whole question, the whole big mystery is, all that is fine, but the energy function is the LLM itself and its parameters. How in the world do you train the LLM? So that requires a little bit of thinking. What you do is, and this part, I think, is a little tricky, so I'd like you to please pay attention. what you do is you take a random state of the E theta, you give it an input, and you take a candidate y hat, and ultimately you do the gradient descent. And what will it give you? It will give you y hat best for this particular energy, given theta, this particular state of the model. But we need to make this transformer learn the training of the transformer. The parameters have to be better. So now what do? Now you can use your standard cross entropy loss. Let's say your loss function is your, think of your basic cross entropy loss or any loss function, doesn't matter. See, for text, you use cross entropy loss. For images, you could use, for example, regression loss, sum squared error loss, or reconstruction loss or something like that. Right? So it doesn't matter. It will be some function of the label, the ground truth, and the y best for that value of theta. And so now you can do, this time you can do a gradient descent of the loss against theta. So you can come up with a better theta is theta minus some other learning rate. Let me just say some other learning rate. Let me just say some learning rate. And this. So what happens is that when you train the model, do you realize that there is double gradient happening? One gradient is finding the best, given these parameters. The inner loop is finding, this inner loop is finding the best prediction given the current theta. And the outer loss function, its gradient is helping improve the theta itself, the model itself. So there is a joint learning taking place in this model. Right? And that is the magic of it. So when you work out the math, you'll realize that what it does is, because there is a gradient here and there's a gradient here, when you look at this equation, you will realize that there is actually a double gradient. It's called a Hessian, and you'll end up with a Hessian, but that's for the people who like the math of it. You'll end up with. Now, there is one more subtlety. This equation that we wrote at line 4 during the inference verification, actually, it helps not to do it like that. But what people found is you use a variant of the Langevin dynamics. In other words, you inject a bit of noise to it. What it does is it sort of gives you a shaky journey to the minimum. By taking a shaky journey to the minima, right? It's a form of, think of it as an energy landscape regularization. When you do this during the learning process, then what they have observed is that instead of learning energy surface that looks like this, you learn a nice smooth energy function, right? This noise perturbation. By the way, the use of this Langevin dynamics are using a noise perturbation in the gradient descent to sort of smooth out things, especially in energy functions, is a long-standing trick. So that is that. I think I have covered everything in the model. What they show is that it does very well. If you look at this picture, number of tokens in billions, that is the amount of data, validation perplexity. In other words, during validation, how confused is the model, how much is the error? You can see that, by the way, they keep using the word transformer plus plus. What do they mean is the state-of-the-art transformer, whatever we have transformer. So when people use the word transformer, implicitly research community thinks attention is all you need, the classic transformer. But since then, much water has flown down the river. People have come up with lots of enhancements to it. Better loss, better activation functions, right? For example, it's with glue, whatever it is, glue, etc., etc. Better positional embeddings, better this, grouped attention. Many, many things have happened in the last few years. The core transformer architecture has been greatly enhanced. So in this paper, when they use the word transformer plus plus, they use it as a shorthand for state-of-the-art transformer with all those enhancements rolled in. So you can see, though it's not, well, obviously, because they have done a first experiment, so the results are not, like, it's not ground shaking, but it does show that if you look at the blue line, it does manage to come crossover and lead to lower complexity, right? And again, depth in the, like, and you can, so the idea is here, of course, depth in transformer blocks, like how many transformer blocks do you have, how deep, how big the model is. And what it is saying is that it is not evident here, but I suppose the idea is that this will go in like this. And if I were to exaggerate, sooner or later, the other line will continue like this. What it means is that at higher and higher model size scales, energy-based transformers will give you much better validation perplexity than the normal is. Though at this moment, the evidence they have created doesn't explicitly show that, but it implies that. Then, similarly, you can see non-embedding. So generally, you see that it seems to have slightly better everything, right? Though I wouldn't say that this is very, very ground-shakingly positive evidence, but it shows that there is a new line of thinking, a very interesting research idea. And if nothing else, it is competitive with the state of the art and beats it slightly. And the idea is that it does induce system two thinking. That's the main claim. This diagram is very interesting. When you look at it, what it's basically saying is, by the way, when they use the word out of distribution data, I would call it a little bit of a misnomer. What they really mean is the validation data, right? So see, what happens is, you notice that number of forward passes. Think about it this way. A regular transformer just makes one pass. You give it the same input, it will keep on producing the same output, right? So obviously, you get this result in a regular feed forward, a regular forward pass transformer, autoregressive transformer. On the other hand, because the energy-based model, it starts out with a random guess. Look at this. It starts out with a random guess. So obviously, it will have ridiculous initial value. Then it progressively makes its way towards better and better and better and better. So in other words, you see the effect of gradient descent towards the minima in the energy landscape. That's all it is, right? The next thing it shows is that it is scaling during training. It scales quite good. Perplexity improves. So when you train it with more and more tokens, right, it's sort of data efficient. It learns, it tends to scale. Though looking at this diagram, the best fit line is sort of there, certainly, but the data is quite spread out. Thinking helps more on, so it shows that they make quite a bit on the thinking part, that it induces thinking. This diagram is actually the last one, and I'll stick with. See, it's quite interesting. It tells you how the model is after thinking over the thing. So suppose let's say that the quick brown fox jumped over the lazy dog. This is what it is supposed to predict. Right? You would now look at this scale, normalized energy. Remember, low energy means high probability, means more confidence. So you want to see yellows. What happens? If you look at this, at the 0th step, obviously it has random guesses everywhere. It doesn't know. For it to get to quick, well, it's hard to guess the word quick, but it's still here. But if you look at quick, it also, it's a darker color. It's much more confident that the word brown is here. After brown, if you look at the word fox, progressively, these confidences improve as you keep going. Now, the other thing that you see here is also another statement, and you see the same thing. System 2 thinking. Thinking is blah, blah, blah. Right? So that's what you see. Right? The color keeps darkening as you progressively move from iteration to iteration. Again, you see the gradient descent in the energy landscape. So that is it. There are a few more diagrams, a few more results, and it shows that it achieves good results and so on and so forth. I thought this result was pretty impressive, that it could do so far better than a diffusion transformer. In 3 steps, it could do it could come up with an image, whereas a diffusion transformer takes 300 steps. That is it, guys. I'll take questions now. So this is a little hard topic. Energy-based models have always been considered a bit hard topic because you're thinking of a model that actually doesn't predict the next token. Instead, it predicts an energy function. It says, give me a distribution, that also a probability distribution, and I'll tell you, convert that probability distribution into a token vector, embedding vector, and then feed it into the input, and I'll tell you energy function, energy value. Right? And you work with the energy function as a verifier and so forth to finally predict the answer. So it's a 2-step journey in these systems. But that is it. That's an energy-based transformer. I think it's a very insightful idea, the way they have implemented it. Though it is always hard to sort of explain this from energy-based models from scratch in such a short time. Let's see, are there any questions here? Oh, there's a famous physicist who swear by them. Walter, would you know his name?
No, I don't. I was trying to think of it. I watched a lecture and I wish I had, obviously I didn't write it down, but it was really interesting and it's good to see you talk about that.
Yeah, Walter. Actually, if you and I happen to have graduate school degrees both in theoretical physics, mathematical physics, and in computer science, AI. So I must tell you, my perspective aligns with physicists. To me, AI is certainly applied physics to quite an extent, especially neural networks, and certainly energy-based models is as close as you get because they are literally using statistical mechanics and Boltzmann functions and so forth.
Yeah, no, I think actually I have a great idea for an app, and the app you mount it on your phone and everywhere you go, and not only will it keep like a history, but it'll like do an intelligent history, and that would also create links and follow links. But I guess that's going over the scope of what I can do in very reasonable lifetime.
Yeah, it's possible. See, people have always believed, as I said, that thinking will come and energy-based models will be somewhere in the picture. So I suppose this paper, if you look at Jan LeCun, he is very big on energy-based models, right? And the IJEPA, VJEPA, energy-based model, world models. We covered that a year or so ago in our paper reading sequence. So people they all try to go. So your thinking is aligned with them.
All right, well, sorry I can't think of it off the top of my head.
All right, guys, any questions? You guys are extraordinarily quiet today. Was it helpful, by the way? I don't know, given how quiet everybody has been. Was it reasonably clear? I know it's a hard topic. Did you get the gist of the paper?
Yeah, if I can speak, at least it's very hard topic, so I'll have to probably reread this paper couple of times before I can make more
Yeah,
sense.
actually, I downloaded it too. I got to read and maybe I should have read it before the lecture.
Yes. It's a paper, though I must also say that it is one of those papers that needs a helping hand to just make your way through it, because they refer to a lot of the background work. They just refer to rather than very clearly explaining it in the course of the paper. I think you guys will have a fun after this intro. It will be a stretch to say that I explained it so clearly that we got it all. But I'm hoping that after this discussion, when you go back and read the paper, first thing is it's really worth reading. I invite you
By
all
the
to.
way, where is the recording for this lecture?
Oh,
there
it
a
is
lo-
on YouTube in Support Vectors channel.
Okay.
Samantha would put the link. And
Okay.
so we have a playlist called Weekly Technical Talks at Support Vectors YouTube channel, and all the paper readings, they show up there. For example, the discussion that happened on Monday is already there, and today's discussion will take maybe a few hours, but by tomorrow or day after, it will already be there. It will get cleaned up and be there on YouTube.
All right. Thank you much.
All right, guys, then. Good night.
Thank you.
Good night.